Yeah, so linear model selection and regularization. So I think that if you have taken 50-30, you have studied the model selection. So I think Bill, you took the 50-30 last semester, and I believe that Shaoli also covered the model selection AIC. Is that right? Yeah. Okay. Great. Yeah. So today we will discuss the several methods. So one is the model selection. That is, for example, the stepwise AIC selection. And also we discuss to use the cross-validation to choose the best set of predictors. Actually, its algorithm is the same, but I just want to emphasize the the use of cross-validation versus use of information criterion. And another method is regularization. So regularization is not the model selection. So model selection is more digital. So suppose that we have 100 predictors and we select the 15 out of 100. So 15 predictors are correct predictors and the other 85 are fake predictors. So we have the 0-1 decision on each predictor. And the regularization is different. So regularization, the idea is all predictors may have some coefficient, but if we allow any coefficients, sometimes we have trouble to have so many predictors with large coefficients, and that may make the estimated, the fitted value, too volatile. So the predicted value too volatile if we have the too large predictors. For example, suppose that we have x1, x2, and estimated model is like 100 times x1 minus 99 times x2. But suppose that x1 and x2 have some measurement errors, then measurement error will be inflated by these coefficients. But if suppose that x1 and x2 are very similar variables, then probably even if the estimated parameter is 199, just using x1 makes more sense because at least it does not inflate the error to measure the x1. So that is a kind of regularization method. So we avoid having the too large coefficients. Oh, okay, so in this case, actually only x1 is included, but suppose that maybe 1.1 minus 0.1 x2 or something like that. X2 has some information on the response, but still that we want to keep these coefficients smaller by some algorithm. So that is regularization method. So model selection is, okay, x1 is useful than x2, so we only choose x1. So that is the idea of model selection. Regularization, okay, so both variable may be useful, but we want to avoid the too large coefficients. Have you ever studied the regularization before in another class or in your job? Yeah, so we discussed how to determine the best model among linear models. Actually, they're not necessarily linear models, but just for simplicity, we stick with the linear model for now. And x1 to xp are some predictors. Yeah, okay, so this is very basic concept, and the training error is always smaller if model is bigger. So yes, actually this one and this one, the left-hand side and the right-hand side are almost the same graph. And here the number of predictors, in some sense, we include x1 or x1, x2 or x1, x2, x3. And probably this is the number of predictors, so it includes intercepts. So if we fit the predictor, the response on only intercept, then residual sum of squares. So summation of epsilon I hat square. So this is this size, but if the model gets more predictors, then error gets smaller. And this is training error. So if we have more predictors, then we have always the smaller the residual sum of squares. And right-hand side, basically, we have the same thing. So this is the R square, non-adjusted R square. So R square is basically the percentage of variation explained by the predictors. So that is always larger if we have more predictors. So if we have one more predictor, I mean, if the set of predictors includes the previous set of predictors, always the model performance gets better, or at worst, it's the same. So R square adjusted, R square is also increasing over time. So always the larger number of predictors, the fit is better for training set. So with only the training set, we cannot see which model is the best. So there are a couple of ways to formulate what is the best model. So what is the best model? So one natural way of thinking is the best prediction model. So we minimize expected test error. So suppose that we have 100 observations only, but if we train the data, then what is the best model to predict another 10,000 observations? Then we can evaluate the performance. Even if we have very small training error for existing 100 observations, if we have new 10,000 observations, maybe error gets larger because of the overfitting of the model. So best prediction model is the one most natural way to think about the best model. And another thing is the true model. So we want to see the truth. So assume that there is a correct model among all our candidate model, and we want to identify the correct model with an increasing probability as n goes to infinity. So the true model may be a vague concept in real world, but suppose that we are doing some simulation, and okay, I'm playing a game with you, and I have data for x1 to x100 for maybe the 10,000 observations. So these are 100 different predictors. And I just handpick some variables and define y, and y is equal to, for example, 1 plus the 2 times x1 plus the 3 times the x75 minus 5 times x99. So in this case, then I add some large noise like epsilon. So in this case, the true predictors are x1, x75, and x99. But maybe, for example, the x10 is very similar to x1. So that if you estimate the best regression model, maybe you decide to include x10, maybe in addition to x1. Or maybe you miss x1 and you choose x10. So that's possible, especially if we have large number of candidates, that probability gets larger. So another interpretation of the best model is the true model. So suppose that I develop this model and I know the truth, and you have to guess what is my model. Then you have to guess from this data set, as well as the response variable, and what is the best way. And yeah, it really depends, but but it's different from best prediction model. So for example, suppose x10 is very similar to x1, and you have x1 and x10, and both have high correlation with y, then just in case, maybe you want to include these two variables. Or maybe the y has some vague relationship with x31. And you wonder whether or not you include x31. And if you wanna find the best prediction model, if y has some relationship with x31, probably you will take this x31. But if you wanna get the true model, especially if you know only a few predictors are chosen in this model, then that if the true model is small, if you know the true model is small, probably that you don't want to include x31. So suppose that, for example, x31 has p-value of 0.09, 0.08, or 0.09. Then, okay, so this is a kind of significant at 0.1% level, but if we have 100 candidates of predictors, basically on average, we have 10 predictors whose p-value is less than 0.1, even if these are not related to y at all. We have 100 predictors, so 10% of them should have p-value less than 0.1, even if it's not related to y. So finding the best prediction model and finding the true model are different objectives, slightly different objectives. And generally, best prediction model is larger and more complex than true model, because the best prediction model keeps variable which makes prediction marginally better but are not significant. And true model is simpler and more interpretable than the best prediction model. So sometimes even if we don't know whether there is a true model, still we want to get different method than best prediction model, because best prediction model is too large. So yeah, it is somewhat vague, but the best prediction model is not always our best objective for the best model. So we discussed the 3 different methods: subset selection, and shrinkage, and dimension reduction. So the first one, the subset selection, this is what this 5030 discussed. So choose the subset of size D of all P predictors, as we discussed in stepwise selection. So suppose we have maybe 100 predictors and we choose some best subset, maybe 23 predictors, something like that. And shrinkage method, we use all predictors, but make the coefficients smaller. So if usual ordinary least square model estimates the y is equal to 1 plus the 2x1 minus 3x 10 plus the 5x 90 plus epsilon, but we shrink these parameters to 0. Maybe we make this 2 into 1.8, or this negative 3 into 2.5. Maybe 5 to 4 and a negative 3 to maybe 1.2, and 2 go to 0 or something like that. So this is a shrinkage method, because the coefficient shrinks to 0 compared to the least square estimate.
Do we do all of those, or is that done systematically?
Systematically, we will do that, yes. We will discuss the algorithm later. Yeah. And another method is dimension reduction. So suppose we have 100 predictors, and that is so hard to deal with. So we want to summarize those data set. For example, suppose you want to forecast the next quarter's the GDP. And we have unemployment rate data for 50 states. Then, okay, so each number affects probably the GDP for the next quarter, but usually, just average or some weighted average of the 50 unemployment rate has sufficient information to predict GDP. You don't really have to introduce all 50 variables as predictor. So in such a case, maybe you take the weighted average. So that is a kind of dimension reduction. We originally have 50 dimensional data, but we make it just one variable. So that is used in many places. So for example, in time series analysis, that you combine several variables into one. And sometimes, like image analysis, we use also the dimension reduction. So for example, we have the 100 images of the same teacup. Then of course, depending on the angle, the picture looks different. But the angle is determined by just a three-dimensional number, maybe two-dimensional number. Maybe it depends on how you formulate it. Maybe if only direction, maybe two-dimensional. So that means, suppose we have 100 pictures, and each picture has maybe 100 by 100 pixels, so 10,000 pixels. Maybe red, green, and blue scale, so RGB scale. So we have the 3 layers of 100 times 100 pixel pictures. So that means the P is equal to 30,000. But if we take the pictures of the same teacup, basically the essential information is only two-dimensional because that is only direction. So in such a case, this 30,000 variables is summarized into essentially the two-dimensional vectors. So in such a case, to do this, the simplification makes some prediction better. So yeah, for example, I don't know, but so depending on the angle, we will decide, for example, so which angle can keep at least half of the water in the cup or something like that. Then that is basically binary decision-making problem, right? So with the 30,000 pictures, but essentially the important information is two-dimensional. So we do the dimension reduction first, then we do only the two-dimensional data to predict. Then probably that makes the prediction better. So that is the dimension reduction technique. So often used for image analysis or high dimensional data analysis. Yeah, and shrinkage and the dimension reduction are particularly useful when the number of predictors is close to n or even larger than n. So the example of this, the image, the 100 images of teacup data. So we have basically the 3,000 dimensional data, but we have 100 pictures, so n is equal to 100. So for that problem, basically we have to use either shrinkage or dimension reduction. Otherwise, we cannot really solve the problem. Suppose n is only 3 and the p is 10. If p is larger than n, then usual method does not apply because we have 3 observations and we have beta naught plus beta 1x11 plus beta 2x21 up to beta 10(1) x10 plus epsilon 1 and so on. In this case, we only have 3 equations, but we have 11 coefficients. So that means we have infinitely many ways to determine these coefficients to make all errors equal to 0. So in such a case, these coefficients are not determined. So we have to add more restrictions, such as shrinkage or dimension reduction, to uniquely estimate this model. Yeah, so not always there is only one solution, but still we have to find some solution quickly and efficiently and meaningfully. So that is often the case in engineering or statistics problems. Yeah, for example, the robot. I think my older brother is electric engineer, and when he was a master's student, he was doing some analysis on image, but he's also thinking about the robot arm problem. So robot arm have the many joints, like the flexibility of 5 flexibilities, So basically the degrees of freedom is 5, but the robot is in 3-dimensional space. So there are multiple solutions to reach certain point with that robot arm, but still they need a solution. They need a unique solution to make the robot arm to reach the specific place. So not always P is smaller than N. So that is the point. And in such a case, we need a different algorithm. So if P is smaller than N, then, for example, OLS determines the unique solution, but if P is larger, if it's not the case. Okay, so subset selection. Do you have any questions so far? So we are studying these 3 methods. Okay, so subset selection. So there are 2 approaches. So one is the best subset selection, and the other is simplified method. And best subset selection is very fundamental. So try all subsets of the entire set of predictors and choose the model with minimum criterion. Here, the AIC or some other criterion. So this takes time because it takes time order of 2 to the power p. If p is equal to 10, we have to examine 2 to the 10th power, so 1024 models. So suppose we have x1 to x10. We have to decide whether or not x1 is included. So 2 cases, 2 possibilities. And whether or not x2 is in the model. That is 2 cases. So 2 times, 2 times, 2 times. We have to multiply 10 times. So we have the 2 to the 10th power. So 1024 models. So if we only have 10 predictors, that's fine. We can estimate the 1000 times. But if it's larger, it's a problem. So yeah, I heard about a project to choose the best subset of predictors to predict some inflation or something when I was working in a bank. And I heard that so my friend was in the project, and that there are 32 possible predictors. And the 2 to the power 32 is about 10 to the power 9 times maybe 4, right? So that is pretty large. So 4 billion combinations. Yeah, and at first my friend's boss, they mentioned that you should try all combinations. So 4 billion, and my friend said that it's impossible because of computational power. Then the boss suggested, okay, then how about 30? But it does not make much sense, 2 to the power 30. Maybe, the time is, just 1/4, 1/4 of the original size, but still they have to try the 1 billion times. And that is not possible. So we have to have some more efficient way to choose the predictors. So that is the stepwise selection. Probably you have already studied in Stat 5030 or another class. And the stepwise selection is start with a certain model. For example, just model with intercept. That is one case. Or a full model. So y is a function of x1 to xp, the whole model, or some baseline model. So some prior information gives us x1 and x2. So we know that x1 and x2 are useful, but maybe we don't know other predictors. So starting with this model, we want to see the other predictors are useful. So some base model, then add or delete one variable at a time to minimize some criterion. For example, AIC. So there are three types: the forward selection, backward selection, and a combination of the two. For example, that we start with x1 plus x2, then we add another variable, either x3, x4, up to xp. And suppose that x5 is chosen, and we add another variable, either x3, x4, x6, or x something. So we add one variable at a time. And another way is backward selection. Suppose that we start with the full model. We drop either x1, x2, or x3. The most useless variable we should drop first, and we continue. Or a combination of the two. So for example, x1, x2, we start with x1, x2, then we get x1, x2, x3. Then we can add x4 or x5, but also it's possible that with x2 and x3, we have enough information and x1 is not necessary. That's possible. So in such a case, that we go back to x2 and x3. And then maybe x2, x3, and x5, and x2, x3, x5, x8, or something like that. So both go forward and backward. Yeah. So which method is fastest, do you think? Suppose that the forward selection starts with the null model. And backward selection starts with the full model. And the combination of the two start with some fixed model, just maybe from full model or null model or whatever. So which is the fastest in practice? I think I asked this in another class, maybe 6840 or 5030. I don't know.
I would say combination. Some sort of relationship. I would probably think of a design of experiments, but I'm not quite sure if that would work in this kind of situation. I don't see why it wouldn't.
Yeah, my question is, which is fast? Oh, actually, I thought that, no, yeah. Which is fastest?
I say my guess would be that the forward and backward direction would probably be similar, because I would think if you have like n predictors, then you have to try well, then you fit n models for the forward selection method, keep the one that has the lowest AIC, for example, and then repeat with the remaining n-1 predictors. But if you do the backward selection, my gut's telling me that you would have to do the same thing, right? Because you would start off with your n predictors, and then you would remove one, then you do that n times, then you keep them all with n-1 predictors that has the lowest AIC and continue. So I feel like it would be the same number of steps for forward and backwards, but maybe not.
How about combination?
Yeah, I'm not sure. Maybe that's faster.
Yeah. So actually, that is my one mathematical way of thinking, right? So that if you think about the graph for the forward selection and backward selection is basically similar, but actually, in fact, the forward selection takes much less time because simply the model is smaller. So backward selection, so we have suppose 100 predictors. And at least, for example, maybe 15 years ago, if you use the backward deletion with 100 predictors, the computer stops at that point because 100 predictors is too large number. And the forward selection, we start with the smallest model and we add variable. If the final model is really large, like all 100 variables, of course it is slow, but suppose that final model includes only 10 variables, then forward selection is quick. So forward selection is much faster. So that is actually, I think, at least, yeah, practically important point. And backward, slower. Combination of the two, of course, it depends on the what model we start with. If the original model is small, it may converge first. But of course, it's slower than forward selection usually because we go both ways. But it's probably similar as long as starting model is similar. Yeah. So in terms of the number of iterations, the forward selection and the backward selections are similar, so they're basically same. But the actual computational time is much faster for forward selection because each model is simple. So that's the reason. Yeah, so forward selection first. Okay, so suppose that we use either forward or backward selection, maybe forward selection. So what's the maximum possible number of models we have to examine? Suppose that we have 10 variables. The all combinations, we need 1024 cases, right? So forward selection, at most, how many models we should investigate?
Would it be 10 factorial?
No, yeah. I know why you say 10 factorial, but it's much smaller.
To the 100th.
Yeah, 100 is pretty close, and actually maybe half of them, because at first you have to try 10 variables, and suppose one variable is chosen, x1 is chosen, then we have 9 remaining variables, so we have the 9. Then if we have already adapted 2 variables, then we have 8 remaining variables, so 8. So actually this is the sum of 1 to 10. So this is 55. So about a half of 100. So it's much faster than trying the all combination of variables. So previously, the 2 to the power 32. So this is about 4 billion. But in forward selection or backward selection also, the total number of models is just 32 plus 31 plus up to 1. So sum of 1 to 32. So that is 528. So they're much smaller than 9 billion. Combination of the two, I think probably it's hard to bound the number of trials. We can increase the number of variables and decrease the number of variables. So I think theoretically it's possible to go through all combinations. So maybe we have to try the 4 billion, but practically the most of the time it's pretty fast. Yeah, but of course, not guaranteed to find the best model among all combination of predictors in stepwise selection. Yeah, especially it's true, for example, yeah, x1 and x1 is the most the variable selected first, and x2 is selected second. And then x3, but after that it's possible that the x1 is no longer needed, as x2 and x3 includes most information, so that is possible. So It does not happen often with smaller number of predictors, but theoretically, it does not guarantee to find the best model. So this is stepwise selection. So my recommendation is to go forward selection if you go stepwise. Yeah. And what criterion to choose the model? So basically, in each step, we compare some measure, maybe R square, or maybe the standard size of error, residual standard error, or what. Then the AIC is known as the best indicator if the model is correct. So usually we minimize the disk quantity. So -2 times log likelihood plus the 2 times the number of parameters. So number of predictors is expressed, denoted by D in this chapter. So -2 log of likelihood plus 2 times D. And the smaller AIC is a better model. Smaller AIC means the better model. So how to interpret this? At first, likelihood. Of course, larger likelihood is better. If likelihood is larger for the model, that model is more likely. So likelihood is basically larger likelihood is better. So that means -2 times log of likelihood. So this is, the smaller is better, right? Smaller is better. Likelihood larger is better. So this first term, smaller is better. But here, actually, the larger D includes more predictors. So usually it makes likelihood larger and the first term smaller. Larger model makes likelihood larger. So we have to balance between D and -2 times log likelihood. So if D is large, then first term is going to be small. But if D is too large, then entire term becomes large. So we have to compromise at some point. So smaller model is better, and a smaller first term is better. Smaller model is better. Maybe I should say the simpler model is better. So this entire quantity of AIC, the balance between larger likelihood and a smaller number of parameters. Yeah, so the idea is combining the error size and the penalty for the large model. And some other criterion. So Marlow's CP. Marlow's CP is actually the same as the AIC, but this is specific for the linear model. So if you write down the likelihood function of the ordinary least square model, and then actually this CP is just constant times the AIC. So it doesn't really new method. And another one is the Schwarz-Bayesian information criterion. So it's reported that this model, this criterion is better to identify the true model. And this is defined by negative log times likelihood. This is basically the same as AIC, but plus log of n times d times the sigma hat square. So yeah, so sigma hat square is anyway a constant, some estimated constant. So the log of n is the key part. So last time this penalty term is just 2 times d. But here, basically in terms of order, log n times d. So if sample size is larger, then we have larger penalty on d. So sample size is larger, then we have some variables which have marginally better, marginally significant. But we want to drop those variables, so we penalize d more. So it chooses, this BIC chooses a smaller model than AIC.
Is the sigma hat squared in this situation considered a per model sigma hat, or is that actually, is that, if I were to think of it this way, sigma hat I, where I being whichever model you're using?
Sigma hat I, what do you mean sigma hat I?
Sigma hat squared.
Uh-huh.
Is this situation the sigma hat squared generated from each of the individual models? You said it would be a constant, but it would be, is it a different constant per model?
Oh yeah, yeah. Okay, that's a good point. So I think the sigma hat square is okay. So conceptually, this is the true sigma square, but the true sigma square is unknown. So we have to estimate the sigma hat square in some way. And usually we use the sigma hat square from the, I think, the largest possible model. Oh, largest possible model? Not really. Sorry. I think that's not possible. So it depends on the estimation, but you can estimate sigma square from each model. Yes.
Thank you.
Yeah. So Schwartz information criterion is given by this Schwartz Bayesian information criterion. Yes. And this is one experiment on what model is chosen by each method. And this is basically AIC. First one is AIC, or Marlow's CP. And the second one is BIC. And the third one is adjusted R square. And this one, and smaller is better. And BIC also smaller is better. And R square larger is better. And it sounds that, oh yes, yeah, and adjusted R square for training set. Yeah, of course, training set. And the AIC, it chooses the 6 parameters, 6 predictors. And the BIC chooses 4 parameters. And the adjusted R square have the 7 parameters. If not adjusted R square, just R square, then always this is, the increasing, monotone increasing function. But here, adjusted version, so we have some small penalty. So still it specifies some optimal point, but this is 7. So you can see this is 6 and 4 and 7. So it chooses different models. And empirically, the adjusted R square isn't a good method. Always this method chooses the too large model. So theoretically, usually AIC, sometimes which tends to use a smaller model, so BIC, but this isn't really good. Yeah. Yeah, so this is a method for subset selection, but the subset selection can be done by cross-validation as well. So we check the test MSE. So we don't use CP or BIC, but we use the test MSE. So maybe to make sure this cross-validated MSE. This is another criterion, right? And cross-validated MSE and also AIC, maybe the cross-validated MSE. So these can be used to select best prediction model. So it is known that both choose the same model as the sample size goes to infinity, if assumption is correct. The cross-validation is always the simulation method, so it's fine. But the AIC, we have some model assumptions. So suppose that the original model is correct, linear model with normal error is correct, and still, and also we claim that there is a true model out of the candidates. We can make a true model based on candidates of predictors. Then, if those assumptions are satisfied, the both AIC and the CV get the same results if n goes to infinity. And AIC has benefit because it's much faster, and the CV is computer intensive. But the CV is applicable for any model. We don't need likelihood function. Suppose errors are not necessarily normal, then CV is better. Yeah. So, yeah. So formally, we can say that the CV does not require likelihood function. And practically, we can say that likelihood function is not correct. Still, the CV is, the best method. So basically, cross-validation is safer method to apply because AIC is based on many assumptions. So CV is the much more robust method against the violation of assumptions. So CV is recommended. So yeah, I think in 5030, maybe 6840 as well, I maybe emphasize the AIC too much, but that doesn't really achieve the optimal model if the true model, the model specification is not correct. Yeah, so these days we have faster computers, so CV is more common in many cases. Yeah, so this is a very similar model to compare the BIC and the validation set error and cross-validation error. So yeah, so I think it doesn't have much information, but you can see the cross-validated error and the validation set error. So these are similar. So both are a kind of expected error size, but just in different ways. Validation set error, we have only one validation. Cross-validation have the multiple validation set. And BIC chooses smaller model, so actually it gets smaller model. So I think that practically when BIC is used, usually the reason is there are too many predictors are chosen by AIC. And also, this is the one common situation for AIC. So what if AIC or cross-validated error is very close to each other for many Ds? So suppose we have 100 candidates of predictors. D is equal to 1, 2, 3. Okay, so AIC or cross-validated error that goes down dramatically, like this. But after that, we have very marginal difference, sometimes maybe even increase or something like that. But still, maybe the smallest AIC is achieved here. So then what we should do, maybe just 3 or 4 is sufficient, but sometimes we use we have 50 as d is equal to 50 achieves the smallest AIC. So in this case, choosing the 50 variables does not make practical sense, because with just 4 predictors, we almost achieve the same the same accuracy, the same prediction power. So sometimes the people use the d plus minus 1 standard deviation of the test error. So cross-validated error is simulation method. So we can make a band like this. And suppose smallest 1 plus minus 1 standard deviation. And if this value is within 1 standard deviation, we choose the smaller model. So that is often people do. I think there isn't really justification, mathematical justification behind it, but practically, choosing 50 does not make much sense. Yeah, so that is the subset selection. They have questions. So this book is very practical. So even theoretically, it's not really justified still.
What would, looking at your chart that you sketched on the bottom,
oh, sorry.
You're going from the large to ending at 4. Why doesn't 3 work? Or is that because they're all around the same?
Oh, maybe 3 maybe also works. Yeah, 3 maybe, yeah.
But if we continued on through, would it fail under, or is it because it's no longer low value? The AIC is going up. So you're looking at the lowest value of the AIC. I'm not quite even understanding why the need for the test error plus minus 1 standard deviation.
Yeah, I don't understand either. So the 1 plus minus 1 standard deviation. Okay, so at least we can calculate 1 standard deviation, right? So we can do multiple cross validations. Then we can have, for example, 20 cross validations. Then we have the mean and the standard deviation. So we can make this plus minus 1 standard deviation. So that means that sometimes, the cross validated error is above this, right? With maybe 15% probability, sometimes below -1 standard deviation. So plus minus 1 standard deviation is just, what should I say? So the plus minus 1 standard deviation is still the typical size of cross-validated error for d is equal to 50. Right? So if we consider d is equal to 4 and d is equal to 50, practically d is equal to 50 isn't really a good model. And if the d is equal to 4 achieves almost the same cross-validated error, then practically we want to choose it. 50 predictors, coefficients are much less stable. Possibly we have problem if we have measurement error in X. So I think there are many reasons to choose a smaller model. And while theoretically not justified at all, practically it makes sense to choose a smaller model whose cross-validated error is within 1 standard deviation of the best model.
Okay, that makes reasonable sense.
Yeah. So we don't have any, specific reason that the plus minus 1 standard deviation is okay, but just.
I accept rule of thumb.
Yeah. So that is often what people do. Okay. So next, the shrinkage methods. It's a new method, and we discussed 2 methods: rich regression and lasso. LASSO. And first, rich regression. So usually in linear regression, ordinary least square estimate, we minimize residual sum of squares. In matrix form, that is the y minus x beta transpose times y minus x beta. So this is the 1 by n, and this is n by 1. So basically, that we multiply. So 1 epsilon is 1 minus x beta. So this is just, epsilon transpose epsilon. So this is equal to summation of epsilon I squared. Maybe 2b equals, yeah. So we want to minimize this. So that is usual OLS, but the rich regression minimizes the RSS plus lambda times summation of beta j square. So we penalize the size of parameters. Why? Yeah, because this is the model. So we interpret this later, but the basically large coefficients are not good, because it can inflate error in X, and also it makes model more complicated. And also it makes the many beta j's insignificant, even if it has very high correlation with response. And yeah, you can write this as RSS plus lambda times the norm of beta square. And here lambda is a constant, the so-called tuning parameter. And this is the Euclidean norm. Yeah, sorry, this is lambda. Lambda is a constant, and we will discuss how to determine it later. Actually, the lambda is usually determined by one more layer of cross-validation. So the idea is that we penalize large parameter estimates to make the model more stable. And here is the example of the estimated coefficients. So I'm not sure about the regression. I think that this is the response income limit rating student. I think this is the credit data. So some logistic regression model for the default status, default probability on intercept and income and the credit limit and credit rating and whether or not a student. So we have coefficient for these 4 variables. And suppose that lambda is very small. As lambda goes to 0, this is usual regression, maybe usual logistic regression. So we have coefficients for each variable. So income have coefficient of negative 280, and limit have coefficient of 430 maybe, and rating has coefficient 175 maybe. Student has the coefficient of 120 maybe. And as lambda gets larger, so these coefficient changes. Lambda gets larger, that penalizes the coefficients. So coefficients get smaller in general. Sometimes it gets larger and some other coefficients get smaller, so that's possible. But overall, the coefficients goes to 0 as lambda gets to infinity. So lambda is very large, then basically we have to penalize all parameters, and all parameters become 0, even if the prediction error is very large. So we can see the coefficient shrinks. So coefficients shrinks. So coefficients shrink to 0. And the right-hand side, this is basically the same graph, but it is shown in a different way. So this beta hat is by OLS, usual linear regression. Maybe in this case, logistic regression, so usual logistic regression. But just no penalty on beta. And this is the size of parameter. So the beta hat 2 means the square root of summation. So, okay, square root of beta j square, beta hat square, square. And this is the estimated beta in rich regression with parameter lambda. Yeah, so the same thing. So that means, yeah, actually, yeah, this and this are the same, but basically the lambda is transformed. So lambda is smaller than this parameter. So this parameter and this parameter are very similar. So basically, lambda is smaller. And this way, the lambda gets larger. But just transformed. So this x scale is transformed. So flipped and transformed. So this makes some sense because the lambda, we don't really know the what lambda is large and what lambda is small. So after seeing this, we can see that maybe, lambda of 1/100 and 1/10,000 may not be a big difference. And also after maybe lambda becomes larger than 10,000, all estimates are 0. So we don't really have to think about it. So maybe important thing is from here to here. So we can see. But before we make a graph, we don't really know what's the typical range for lambda. But here its meaning is clear. So if ratio is 0, that means all coefficients becomes 0. So if ratio is 1, then we don't have any penalty. So it's more reasonable scale. So from 0 to 1. And also it has some reason because of algorithm, but you can see that these two are the same graph and the right-hand side. It sounds a little strange, but there we have some reason to have this as the index. I mean, the variable to use for x-axis. And the pros of rich regression against the linear regression. Rich regression coefficients are smaller, so usually it has smaller variance. So think about fitting the polynomial on some beaver temperature data or something. And if we use very high degree polynomial, the estimation looks like this. And it's too volatile. But if we use rich regression, this does not happen. And the estimate is more stable, probably like this. And it also reduces problem of multicollinearity. If we have two similar variables, often coefficients are inflated, but the rich regression avoid this. And the prediction performance may be better for large P or under severe multicollinearity. Not often the case. Usually it gets worse, but if the situation is like we have many predictors and some predictors are very similar, then sometimes prediction performance may get better. And it is applicable when P is larger than N, for which the least square method cannot uniquely identify parameters. Like P is equal to 3, N is equal to 10. We cannot identify parameters. But rich regression determines the unique parameter. So that is why it's called regularization method. So if P is larger than N, usually the problem is singular, but actually this makes the function regular. You can see this. So RSS is a function of beta 1 to beta P, but it's not uniquely determined if N is smaller than P. But if we add this, always we can determine the minimizer. Yeah. anyways, this is the concave function, sorry, convex function, and we have all squared term here. So obviously, if one of beta j's is very large in absolute value, then observation gets, the entire quantity, the loss function gets larger. So we can see we have some point which can achieve the global minimum. So yeah, now that we can see this term to make minimizer unique. So obviously, with this term, the minimizer is unique. And much faster than the subset selection of all combinations. Yeah. So the rich regression works much faster than subset selection. I don't know if it's faster than forward selection. Maybe it depends on the case, but generally the theory suggests the computation is pretty fast. And I don't exactly know the most efficient algorithm for rich regression, so I don't really know their details, but that is the one very practically useful point for rich regression. So that means that with these slides, we cannot really understand rich regression. Okay, so we know the model. Mathematically, we know what to minimize. But actually, we don't know, how efficient this algorithm can be implemented. So we cannot really see the exact reason why rich regression is so useful. But the fact is that it's much faster than subset selection. And the cons of rich against linear regression, the parameter estimates are biased because OLS is optimized in some way. Beta hat is unbiased, and as long as it's linear function of x and y, linear function of y, it's most efficient. But the rich regression doesn't have any of those justifications. So usually prediction performance is worse in traditional example with large n and small p. Yeah. Any comments?
Not at this point.
Not this point. Okay. And here is some conceptual figure. So this is based on simulation. Oh. Yeah, simulation. And we decompose the expected error size, expected test error size into variance part and a squared bias part. And this purple line is total error, total expected error. And this black one is variance, I think. Sorry, the squared bias. Squared bias. And this is variance. So lambda is small, more complicated model. Complex model. So variance gets larger, but the bias gets smaller. Lambda is large, then we have very simple model, stable model. So stable, so variance is small, but the bias is large. And the sum of these two are minimized at some non-trivial point of lambda. So we have to choose lambda optimally, but if we choose optimal lambda, then model performance is optimized. And this is the same graph, but for different x scale. And in reality, in data analysis, we cannot decompose this into two, but we only see this purple line, and we decide the optimal lambda value. And the one thing that it's not natural in rich regression is that if we change the scale of predictors, then penalty term in rich regression changes, because we penalize simply each beta j. So if xj's scale is different, if xj is in meter, but we make it centimeter, then coefficient becomes, of course, beta j over 100. Then penalty is 10,000 times smaller. So it's contradictive. So it's the same model with just different scale of xj, but the penalty is much different. So usually, yeah, so that is this. So usually to make rich regression result invariant in scale of predictors, all predictors should be standardized to have sample variance of 1. So that is usual setting. In computer science department, sometimes even without making a note, they assume every variable is standardized. Yeah, so this is rich regression. And the next one is the lasso. Maybe we cannot finish the entire one, but the lasso is very similar to rich regression, but we minimize this quantity. So RSS plus lambda times sigma of absolute value of beta j. And lambda should be optimized in some way. So only the difference is penalty term. So this is sum of absolute beta j, while rich regression minimize the sum of beta j square. And here, basically the same figure for the figures for the lasso, but the format is the same as the figures for rich regression. So this is lambda value. Sorry. Left-hand side, this is the lambda value, and right-hand side, this is the relative size of parameters. So lambda gets larger, then coefficients that shrinks, but it shrinks in slightly different way. Right? For example, think about the lambda is about maybe 1,500. Lambda is at 1,500 on the left-hand side graph. Then you can see that this coefficient for income becomes exactly equal to 0, while others are positive. Maybe it shrinks, but still positive. And actually, after lambda is 2,000, this orange one and red one also becomes 0. So the coefficients for credit limit and the coefficient for student status becomes also 0. And only non-zero coefficient is rating, credit rating. So yeah, so if we put here this red one, orange one, and black one, so these coefficients become 0. So lasso makes more parameter equal to 0. So this is different from rich regression. Rich regression also parameters shrinks to 0, but you can see with very large lambda, still all parameters are non-zero. So that is a different point. So we have some difference in the tendency. So also you can see the same graph in a different way. Yeah, so lasso has more parameters, parameter estimates equal to 0. So one explanation is that the absolute value is larger than, the beta absolute value of beta is larger than absolute value of beta square when beta absolute value is small. Like the beta is equal to 0.1, then this is 0.1, but this is 0.01. This is if 0.001, then this is 0.00001. Maybe one more 0, sorry. So yeah, so in this case, the much larger penalty on lasso. So if parameter gets small, then actually the difference is large. So beta hat shrinks to 0. Okay. In rich regression, beta is small enough, then it does not penalize significantly. So it remains the positive non-zero. Beta remains non-zero. But the lasso, the beta, it has a power to make many beta equal to 0, shrinks to 0. Yeah, so that is the difference between rich and lasso regression. Yeah, so we continue. There's some more details of lasso and rich next time. Okay, and again, I will assign midterm exam this week, and at least you have 1 week to do it.